by Flavio Ascari, who will present us a new analysis using incorrectness separation logic.
I am Flavio Ascari, and the work is on enhancing incorrectness analysis by reversing direction. So let's get started with the first question: what is incorrectness analysis? And I mean, the idea of incorrectness analysis is I give you this very simple program, and I ask you the question: can this program rise the error, and if so, under which condition? And this is different from, let's say, the usual kind of safety analysis that we do, because our goal here is to identify only real errors that you can find. So we don't aim to prove the absence of errors, but we want no false positive. If we show that an error can happen in our analysis, then that must be also true of the real program. And to do that, we change the perspective from over-approximation to under-approximation. A prime example of one such, let's say, under-approximation analysis is incorrectness logic. And like, roughly speaking, incorrectness logic does a forward analysis. So you start from some precondition that is true in this case that we call P. And you go through the program. And at the end, you reach some post-condition that contains some error. And what the condition of incorrectness logic tells you is that every state in the post-condition is reachable. So in particular, every error in the post-condition is actually reachable. And you can see it here in this, like we call the post-condition Q. So you have that all the error states in Q are reachable. However, the guarantee on the precondition is pretty weak, because in general, P may also contain some states, for instance, this one, that leads completely outside of Q. So you don't know that like, which are the conditions under which the error can happen in an incorrectness logic triple. A way to address this problem is to do a backward analysis instead. So in a backward analysis, you start from the error. Now you don't know that all the errors here are reachable, but by going upwards through the program, you end up in a precondition that is, for instance, in this case, y is equal 0, and you are guaranteed that from any state satisfying the precondition, so from any state in P, you have at least one execution leading to a state in Q. And so if all the states in Q are errors, every state in the precondition can lead to an error. Not that because of non-determinism, a state in P may also reach something outside, but it will definitely have at least one execution leading to Q. Of course, the drawback is that you don't know anymore that all states in Q are reachable, but this is, let's say, the trade-off on the two kinds of analysis. So this helps us in identifying the condition under which an error happens. And I have good news for you. A lot of people have already done backwards under-approximation analysis. So, I mean, we have Lisbon triples, we have outcome logic, we have UNTer, we have sufficient incorrectness logic. But I think there is still some issues with the backward under-approximation. Not everything is completely settled. And I want to show you what the issue is with this example. So the example is still pretty simple. We initialize x, then we have this while loop, and in the end we get to the error. So basically the goal that we are trying to show here is that the while loop terminates. That's basically the problem here. Because if the while loop terminates, then we get to the error. And we start doing this with our backwards analysis. We say, OK, for the while loop, like we start from the error at the bottom. For the while loop to terminate, we need to have here some x that is equal to 0. And to do that, like we use an under-approximation technique that is a finite loop unrolling. Since we're under-approximate, we only care about some execution paths that lead to the error. So finite loop unrolling is a sound under-approximation. And we have some heuristic that tells us, OK, let's unroll the loop 2 times. And so we know that if x at the beginning is a number between 0, 2, and 4, then the loop definitely terminates. And since x is equal to 4, is assigned to 4, then we are happy every initial state lead to the error. However, the issue is that we would like to do this analysis compositionally. And since it is a backward analysis, this means that we analyze the while loop before we have seen the assignment to x equal 4. So we have this heuristic that told us to unroll the loop 2 times. But if we now change the assignment from x equal 4 to x equal 10, we expect our heuristic to tell us the same result, so that we want to unroll the loop 2 times. And if we still unroll the loop 2 times with this assignment, we get a false precondition that is, I mean, it is a sound under-approximation, but it's not very informative. We don't like this result because it's not giving us any information on the initial states leading to the error. And what is the problem here? Well, the problem is non-determinism. And to be more precise, is the non-determinism in the unrolling of the loop. So let's talk a bit more about this non-determinism that is the problem. In general, when you analyze a program, you have two kinds of non-determinism. One is the program non-determinism. That one is, in a sense, more localized because it's usually introduced by, let's say, explicit constructs, either like data flow or control flow that introduces the non-determinism. And this is fine. It's part of the program. We will have to deal with that in some way. And there are ways to deal with the non-determinism in the program. But there is another kind of non-determinism that is the proof search non-determinism. So for instance, in the backward analysis that I've just shown, the non-determinism that we have is introduced by this while loop, because while going backward, you can unroll the while loop any number of times, and so you have to non-deterministically choose how many times you want to unroll this while loop, right? And this is often solved by previous program statements, because if you are going forward, like you see that x is 4 before the while loop, and so you know that you have to unroll it 2 times. But as I said, since we're doing a backward analysis, we haven't seen these previous program statements yet, because they are in the future of our backward analysis. And there are other kinds of non-determinism introduced by the proof search. And one such example is given, for instance, by when you deal with pointers, you have this a lot. And I will show you a more concrete example later, but the point is here, even if you look at these 2 lines, we free y, and then we dereference x. And we have another kind of non-determinism that is introduced by the possibility of aliasing of x and y. So this statement may be an error if x and y are aliased, because we just freed y that is aliased to x. But it may also not be an error if x and y are just different pointers. And so, I mean, this is another kind of non-determinism that happens a lot, and it very quickly leads to a combinatorial explosion in the possibilities, because every time basically you use a pointer, you have to consider all the possible aliasing with all the other pointers that you're talking about. So our goal is to address only this second kind of non-determinism, the proof search non-determinism. And ideally, our end goal is a fully automated analysis. So we would like to give let's say, a way to completely resolve this proof search non-determinism. Before showing our solution, I would like to spend a few words on other approaches, because we are not the first one. As I said, many other people already worked on backward under approximation, and so other people proposed other solutions. And I think most of the approaches are based on a backwards valid forward analysis. So what they do is they do a forward analysis of the program, and this kind of solves the non-determinism because you see that x equals 4 before analyzing the while loop. But they do so in such a way that in the end produces a result that is also valid in a backward sense. So this is, for instance, the approach taken by UNTer, that is a work by Raad et al. Published 2 years ago. And this is an effective solution. It's the theory that is behind some real tool work, so it's an effective solution, but it still needs somehow either some guesses or to backtrack to kind of, let's say, retrofit some assumptions that you find out later that you needed to make the analysis backwards valid. So we propose a different approach to this one that is, as you might have guessed from the title of the talk, is U-turn. And the idea behind U-turn is to get us to do a smart sequencing of incorrectness logic, so the forward analysis, and SEAL, that is like one of the names for the backward under approximation analysis that I showed you before. So the idea is that you take as input an incorrectness logic, so a forward derivation, and you transform this forward derivation into a proof strategy for the backward analysis step. And the point is that you obtain a fully deterministic proof strategy, so we completely solve the proof search non-determinism in the backward analysis. And to do so, we heavily exploit the fact that the forward analysis is done specifically for the program that we are trying to analyze. And so precisely because this forward step is for the program, this allows us to get a fully deterministic proof strategy for the backward analysis. And if you think of this in terms of like the pictures that I showed you before, let's assume you start with this precondition P, you do your forward analysis and you find Q, but in P there are also some of these states that are that don't lead to Q. So what you want to do is you want to kind of follow backward again the path you followed the forward before to find this P prime that is like a refinement of P that removes all these points that we don't really care about. So let's see how it works on an example. This is the same example from before, and as you might have guessed, like the key idea is that, okay, there is this x equal 10 in the code. So in some sense, I should be able to know how many times I want to unroll the loop. And if you do a forward analysis, in fact, it is pretty easy to see that, like, since x is assigned to 10, you unroll this loop 5 times. So let's suppose we are given this forward analysis, and we now like use that as a guide for the backward analysis. And the backward analysis will start again from the error and then arrive at this point, and it sees the while loop, and then like we have to decide how many times we want to unroll this loop. But the answer now is trivial, because like the only thing that we have to do is to go in the forward analysis and look how many times did the forward analysis unroll the loop, and the forward analysis unrolled the loop 5 times, and so we do the same in the backward analysis, and we find this x equals 0, and so we complete the proof. And note that if we change this x from this assignment from x equal 10 to x equal 4, then the forward analysis will unroll the loop 2 times, and so like even going backward again, we will unroll the loop 2 times, and so the things will check out. To go on a slightly more involved example, this one as pointers. So this is a model of the pushback function, the C++ standard library pushback function. So the idea here is this V is a vector. X is a reference to the underlying buffer of the vector. With the pushback, what may happen is that non-deterministically, if there is not enough space in the underlying buffer, we reallocate the underlying buffer of the vector. But this invalidates the pointer x, and so when we try to use x here, we get an error. So for this example, I will use the, let's say, assertion language of separation logic. If you're familiar with it, you probably know already what this means, but roughly it says that x is an invalid pointer, and separately, the rest of the heap can do whatever, so we are not really worried about what the rest of the heap does. We are only, like, the only thing that we require is that x is an invalid pointer. And this is our error condition, because if x is an invalid pointer, when we try to the reference, we get an error. So we just focus on the body of the pushback, and if we do our backward-only analysis, so this is without U-turn, this is just to show you what happens with the backward-only analysis, we get these assertions, and I want you to focus just on the free statement. As you can see, after the free statement, x is deallocated, and this can happen because of 2 things. Either x was already deallocated before the free statement, and y was a different pointer, so x and y are not aliased, or, and this junction means that these are kind of 2 program paths that we have to explore. And the second program path says that, okay, x was not allocated before. In fact, x was aliased to y, and before x was allocated, the same as y, but then the free statement introduced this deallocation. So in this very deterministic sequential program, we already have some kind of non-determinism that is introduced by the proof searcher. So I mean, this is really a problem that you see a lot when you try to do this backward analysis. And how does U-turn solves it? Well, for U-turn, we now assume that we have a forward analysis. And so if we analyze this fragment again, we will see that we will start with like our precondition in the forward analysis that says that V points to X, because we see this assignment first. And so we'll get this assignment where, like this initial state where V points to X and some other conditions, and then we go on, and then we go on with the rest of the analysis. And the point is that since we already know that V points to X at the beginning, when we do this assignment, it's trivial in the forward analysis to see that now X and Y are aliased, right? So the forward analysis kind of knows that X and Y are aliased. And so what happens when we do the backward analysis? Well, we start from the end, and we do one backward step before this assignment. So here already we get some information from the U-turn proof, let's say from U-turn. And you can see this because here we assign the thing pointed by V. So before, like when we only did the backward analysis, we could only say that V pointed to something. Like it would have been a sound thing to guess that V pointed to X, because this is an under approximation. We can choose our path. But of course, like in general, like how do you guess that V points exactly to X? But in this case, we know that V points to X is the right guess because you can see it in the forward analysis step. If we go further with the backward analysis, we now see again something similar. We assign Y, so we had no idea about the value of Y before the assignment, but we can add this guess that X and Y are alias. This is a sound again under approximation, but let's say the motivation why we add this guess is precisely because we can see it in the forward analysis. And this allows us, like in the previous step, before the free, to only consider the case where the two are aliased, and no longer the case where Y is instead a separate pointer, a different pointer from X. And so, like in this sense, we solve the non-determinism by like, let's say, asking the forward analysis what we had to do. And so in the end, we get the full derivation for this program. So I hope the two examples gave you an idea of intuitively how U-turn works. Now to go a bit more on the, let's say, technical part for the last 5 minutes. In U-turn, we use judgments of this shape. So in the gray box, you have the forward derivation, the incorrectness logic derivation, and we don't only consider the final triple, PRQ, but we consider also delta, that is the entire derivation tree. So, like, as I said, we don't look just at the result of the forward derivation, but we want the entire derivation. And we use this part in the gray box, that is the input of the U-turn, to guide the proof, the backward proof, that is this P prime RQ prime. That is instead the backward analysis. And an example rule is, for instance, the if rule. So think of this as a backward analysis. So you start with this Q prime, and you want to find a suitable P prime for this if statement. And when you have an if, you have a choice. You can analyze the then branch, you can analyze the else branch, or you can analyze both. And when you have to decide which ones to analyze, to answer your question, you just look inside your input, inside your gray box, and you see, OK, the forward analysis decided to only analyze the then branch, only C1. So I will do the same. Also in the backward analysis, I will only analyze the C1 branch. And you will use, let's say, as input for the analysis of the C1, let's say as a guide, you will put in the gray box the remainder of the derivation that you had for the forward analysis. So do you have this kind of rules? We have similar rules. For instance, this is what brings you to like the same number of unrolling in a while loop, because you will basically unroll as long as the forward analysis unroll the loop. So this is a proof strategy for the backward analysis, and you may wonder how good of a proof strategy this is. And we have a theorem in the paper that is that we call the progress theorem, that says given any incorrectness logic derivation delta, so whatever is let's say the thing that you put inside the gray box, then there exists a non-empty P prime such that P prime implies P, and you can prove the corresponding U-turn judgment. So if you want to look at it in terms of these pictures, it's exactly what I was telling you before. You start with this P that finds a Q going forward, and then you go back and you find this P prime that is a refinement of P that removes all the quote-unquote bad points in the initial state. And the proof is effective, is an algorithm to compute this P prime. We have a lot more stuff in the paper. We have a lot of rules. We have more examples. We have more comparison with this other approach that I mentioned before, the backwards valid forward analysis. And lastly, one thing I would like to focus on is the last point, is the fact that instead of just considering this idea of using a forward analysis to guide a backward one, we use the same shape of judgments to use the backward analysis as a guide to get a proof strategy for a forward analysis. So by using the same shape of judgment, we could also, let's say, combine the two logics in the other direction. And roughly speaking, this is useful because maybe you start from a set of errors that you think may be reachable, and you want to find both initial states leading to this error, but also to refine this set of errors to only find the ones that are actually reachable, because you don't want just like, you guess the set of errors at the beginning. So to conclude, what we did in this work was to show how you can use a forward derivation to guide a backward one, or also like to do the opposite. And in general, we also think that the shape of the judgment that we introduce, or this idea of combining like proofs in different proof systems can be like something that is worth exploring more in the future. And that was it from me. Thank you for your attention, and please ask questions.
Hi, thank you for the talk. So I'm curious if you can say how this approach compares to bi-abduction, where you also do a forwards analysis, but while you do the forwards analysis, you're refining the precondition. Okay, so that's a very interesting question, thanks. By itself, bi-abduction is not exactly like an analysis algorithm, is more like a way to infer the precondition. So I will try to relate this with what Infer does, that is a tool implementing bi-abduction for this goal. So as far as I understand, like how Infer works, I haven't checked the code, but the idea should be that roughly that Infer uses some logical variables that keep tracks of the initial states, the initial values of basically everything that you have, and then like by going forward, it like adds some frames that you can add to the precondition that that only talk about these logical variables, and you can do that because the logical variables are not like modified by the program ever, because they are logical variables. So in this sense, you kind of have this implicit relation that is given by, okay, whatever transformation you had during the program between like the current value and the initial value, and you kind of add a frame talking about this. In our approach, what would happen is sort of like when you, for instance, you get a condition and you have to backward propagate that, you kind of actually just execute the program backwards, and you find out roughly the same condition in the initial state, but I would say like more, let's say more, yeah, I mean, it's instead of, like, in one sense, you have the forward computation, and then you put a condition on the forward computation. In the other sense, you start with the condition, and you do a backward computation starting from the condition. So, like, you get slightly different representation in the precondition of let's say, the same constraint.
All right. One last question, maybe?
Sorry.
Go ahead.
Hello. Sorry.
Oh, okay.
I have a somewhat similar question. Well, first of all, that's really cool. Have you thought about how to automate / implement this into a tool? Because that seems like carrying around a proof tree is quite expensive.
Okay, so yeah, we have some idea, but we haven't worked on a full implementation, so it's just, let's say, theoretical rambling at this point. But the idea would be, like, instead of doing a full forward analysis, the thing that we were talking about is, okay, you start doing your forward analysis, but whenever you find one such condition that would require, like in an incorrectness logic analysis, this condition, you can add them by using, for instance, the consequence rule. Whenever that would happen, you can instead like start in parallel like a backward analysis that backwards propagate that just, let's say, the propagate that condition to the initial, let's say, to the precondition of the, for instance, of the function summary. And so like this would allow you to, well, first do this backward propagation in parallel. This is always nice. And second, like you should only keep like proof trees of relatively smaller part of the programs that are like matched to the summary that you're computing. That would be the idea.
That makes sense. Thank you.
All right. Let's thank the speaker again.